Hi, Mick McQuaid here, welcoming you again to day 2. This is my second video of day 2 of iste780. And before we move on from where we left off with this picture of reducible and irreducible error, I just want to draw your attention to the hat notation. So the F here and the Y have little circumflexes or carets over them that are pronounced hat in the kind of disciplines that use this notation. So we say that f hat is an estimate of f, so that we're saying that the machine that we suppose, the model that we create, is an estimate of the real model. And we estimate y by using some data. And we have two kinds of data, or I should say we have a maximum of two kinds of data. In supervised learning, we have training data. And this training data consists of inputs and outputs. It consists of an X and a Y, or possibly many X's and a Y. Of course, in unsupervised learning, let me just briefly show you a picture of unsupervised learning from yesterday. We don't have that. In unsupervised learning, here's a picture that we looked at briefly yesterday. We have only inputs. So in this case, the let's see, what is this? This is cell lines. So each one of these corresponds to one of 64 cell lines. And these cells are associated, the gene expression in these cells is associated with some kind of cancer. So in the picture on the left, there have been colors associated with these just based on appearance. The authors have simply colored these because these look like they might be part of a group. These look like they might be part of a group. They've performed some kind of clustering analysis, and they've just done that. Over here, however, they've done some coloring on the basis of the actual types of cancer, coloring and symbols. So I should point out that, for example, a green dot is different from a green triangle. A red dot is different from a blue dot. So there are both symbols and colors at play here. And these refer to, I think, 14 different types of cancers. So there should be 14 different kinds of symbols here. And we see that there is there appears to be some connection between the kinds of cancer and the grouping that we've made. But this grouping is entirely of input variables. There is no output variable here. Cancer isn't really an output variable. These are all associated with some kind of cancer, so cancer isn't really an output variable. So we have, at best, we have an input and an output variable, and that's in the case of supervised learning, which we'll be talking about through Chapter 9. Only in Chapter 10 will we be getting into unsupervised learning. And in supervised learning, we'll have this training data that consists of an input and an output. And it is using this training data that we develop our estimate. Okay, now let's talk a little bit about the estimate. I'm just going to move over here to how do we estimate. And there are two ways. We can think about estimation as being either parametric or non-parametric. And we can think about parametric methods as being methods that assume some kind of distribution, such as the normal distribution. If we know that a process follows the normal distribution, that gives us a tremendous amount of power in making predictions about it, because we know something about the likelihood of anything that happens within that distribution. So a parametric method involves some kind of distribution, some kind of known process. For example, when people wait in line, we expect the time that it takes people to be served in line to follow a Poisson process, or the time that it takes for lines to form or for buses to come follow a Poisson process. And so there's a distribution associated with that. There are all kinds of things for which we know or somebody knows. maybe you and I don't know, but statisticians have figured out over many years of study that a lot of processes follow certain patterns, certain distributions, and we call these parametric methods. And so this reduces our problem. It's very nice because it reduces our problem to estimating the parameters. So what we do is we form a model and we estimate the parameters of the model. And the most common way of doing this is ordinary least squares. And this is a parametric approach. And let's take a look at a picture of this approach, and then we'll look at a picture of a non-parametric approach in contrast. So this particular approach, oh, sorry, let me add the caption here. So this particular approach is an example of linear regression based on two inputs, years of education and seniority, and one output, income. And all these lines are error lines from this surface of this model, f of y equals f of x1 plus x2 plus epsilon plus an error term. And there's a certain amount of error associated with each of the predictions here. So this is a parametric method. And a non-parametric method is shown here. So this is a method that we'll learn later. And this non-parametric method is a much better fit to the data. You see that it's much closer to the data. It's a much more complicated surface. This thin plate spline is very closely aligned with all the data. However, it's very complicated. This surface is a complicated surface, and it's very difficult to explain what's going on. In this model, it's very easy to explain what's going on. In the other model, it's very difficult to explain what's going on. And that brings us to our next concept. Our next concept is flexibility. So, and there's a picture to tell us a little bit about flexibility. What is this, a rough? So here, there are actually two different, oh, okay, I see, a smooth thin plate spline and a rough thin plate spline. And the rough thin plate spline makes no errors. Okay, so, and is very difficult to interpret. Okay, now, interpretability has to do with what we can say about the model. With linear regression, we can say a lot about what's going on. The machine is very transparent. This is least squares. This is right here. It has a very high degree of interpretability, but it has a low degree of flexibility. So the number of shapes that we can portray with ordinary least squares are quite limited compared to the thin plate spline here. We have many, many shapes that we can use to fit to this data using this method, but very difficult to explain this shape. It's very difficult to talk about this shape. It's very difficult to make predictions. With linear regression, we can just go to the proverbial, cigar chomping boss and say, hey, for every 1 unit of X, we get 3.2 units of Y. That's a real easy, well, it's not easy on my voice, but it's a real easy kind of explanation to make. But the explanations that we might make using some of these other methods are completely mysterious. So these are extremely flexible and not at all interpretable. So so when we spoke of the difference between prediction and inference, this is what we're talking about. If all we want to do is predict, we might be better off with these, but if we want to do inference, we might be better off with these.